Welcome and thank you for joining 2020 State of the Science Report. Before we begin, please ensure you have opened the WebEx participant and chat panels by using the associated icons located at the bottom of your screen. Note that all audio connections are muted at this time. If you require technical assistance, please send a chat to the event producer. With that, I'll turn the conference over to Andrea Copping, Pacific Northwest National Laboratory.
Thank you so much, Anita. And thank you, everybody, for joining us this morning or this afternoon, depending on the time zone you're in. My name is Andrea Copping, and I'm a research scientist at Pacific Northwest National Laboratory. And along with my co-editor, Lene Hemery, also at Pacific Northwest National Laboratory, we want to present to you the recently released Ocean Energy Systems Environmental State of the Science Report dealing with environmental effects of marine renewable energy development around the world. We do work for the Pacific Northwest National Lab in the U.S., but we represent a much larger group of analysts and scientists around the world that have put this together. So I don't want to make it sound like we did all the work. So a little bit of background here before I get into what the report actually says. OES-Environmental was, until last August, was known as Annex IV, in case that rings a bell. Now, Ocean Energy Systems is a group of 25 nations that have come together to try to forward marine renewable energy. That is largely wave and tidal energy, but it could be other forms as well, trying to establish this as a good low-carbon energy source. It's part of, and they come together under the International Energy Agency. OES-Environmental is a task under Ocean Energy Systems, and I will be referring to OES, and I'll also use the acronym for Marine Renewable Energy of MRE. I'll try to keep the other acronyms out of it, though. So the purpose of nations coming together under this OES environmental task is to look at environmental effects of marine energy very much with the purpose of trying to forward this industry and establish it so we get this new renewable energy source. And we do this not just as a research exercise, but to understand the risks that may come from marine renewable energy so that we can facilitate consenting or permitting around the world. This helps countries be involved with efficient government oversight. The purpose is to ensure that data and information that are brought together are widely accessible and to proactively facilitate knowledge transfer. Now, OES Environmental has been going now for 10 years. We had a first phase that went from 2010 to 2013 and culminated in a report, an initial report looking at some of these potential effects. From 2013 to 2016, we had a second phase with a number of countries that culminated in the first State of the Science report. And we're just finishing up phase 3 here in 2020. It was a 4-year phase with this 2020 State of the Science report. There are 15 nations who have participated in this process. And we have applied to Ocean Energy Systems for a 4th phase, and that permission is pending, but we've been given indication that we will go on because we simply haven't solved all of the problems. So as far as the OES Environmental 2020 State of the Science report, this report summarizes major stressor-receptor interactions. And by that I mean stressors are that part of a marine renewable energy system, a device, a mooring, a foundation that may provide stress or injury or damage to marine animals or habitats. And the marine habitats and animals are those receptors. So it's how those parts of the system come together with specific animals or habitats that we examine. We're also, in this particular version of the State of the Science report, looking at environmental monitoring technologies. And we have a series of management and planning measures that can help put the science to work to improve consenting or permitting processes. A total of 30 authors have come together from 4 countries to prepare this report, and we've had a lot of extensive expert review. You can see scientists and engineers from 11 countries. We have actually responded to over 1,900 individual comments. And this report serves as an update and a complement to the 2016 report. It was just released on Monday, June 8th, which was World Oceans Day, and we consider this a public draft, so it is open for comment, and the final will be released in September. And there you see at the bottom of it the URL for where you can find this report and all the other pieces, but I'll repeat that a couple of times so you can find it. Okay, now I mentioned stressors and receptors. Over the past 10 years, the scientific community has come together around 7 types of stressors, and part of this report is organized in this fashion. Those stressors are collision risk, the potential for animals to collide with and be hurt by turbine blades, underwater noise from operational devices that may disturb animals, electromagnetic fields coming from power export cables and energized parts of systems may affect some animals, particularly on the bottom. Habitat change, both on the seafloor, the benthic habitat, and in the water column are of concern. Changes in oceanographic systems, the flow, the circulation, changes in wave heights, and the potential for large marine animals to become entangled or entrapped in mooring lines and cables. Now, the last stressor here, displacement, I'm going to say very little about the rest of this time because the concept here is that with many, many marine renewable energy devices out in the ocean, this may displace animals or provide a barrier to those animals reaching their preferred habitats. We really cannot study these because the state of the marine renewable energy industry is such there simply aren't many devices in the water. The most we have in any locations really are 3, 4, 5 devices, and generally they're 1s and 2s at this point. So this is something we'll keep an eye on for the future, but we don't really have much to say about it now. Okay, this is the report itself. This is an over 300-page report, so there's a lot to it. It's made up of several sections, sort of introduction, background, questions. The section B is sort of the meaty part of the report that looks at the interaction of these stressors and receptors. Section C looks at environmental monitoring technologies and techniques. Section D are these strategies for helping to accelerate consenting and permitting for planning and management. And section E is really looking ahead, a summary and path forward. So what I'm going to do for the bulk of the time here is go through these chapters and just give you some really high-level sort of outputs from them. So Chapter 1, which is Marine Renewables and Ocean Energy Systems, really introduces this whole concept and what OES has been doing, why we're doing the state of the science, and so on. And although we talk in most of the report about potential effects, generally negative, of marine renewables, we also need to acknowledge the benefits of marine renewables. From the environmental point of view, that is very much associated with climate change mitigation, a low carbon energy source. But there's other very important benefits, including the potential for development and jobs, especially in sometimes quite remote locations where other industries aren't really placed. And although much of the effort until quite recently for marine renewables has been associated with trying to develop utility scale or grid electricity for the national grids, there has been more recently a real push to provide power from marine renewables in smaller amounts, sometimes far out at sea or in remote locations where there simply isn't other choices. Right now, marine renewables are far too expensive to compete at the national grid level, but in some of these other applications, aquaculture, ocean observations, it becomes really the only viable energy source, so there's a real path forward. But the bottom line, if we look at really the highest level we can look at for really this whole report, is how important it is to cite these developments in the right place and to do it responsibly. Make sure that we are not going after some of the more vulnerable populations and habitats. The table here is just to kind of let you know that I'm talking about this main report for State of the Science, which is very much aimed at the research community and science-based regulators. It is online now at the link I showed you before. It's downloadable as the whole 300-page report or chapter by chapter. But in addition, there is supplementary material uploaded there as well, again focused at the science community. And these are the parts that really, there was too much information for the book, and so it's there as supplementary material. There's also an executive summary uploaded there, which we think of as perhaps really addressing interested stakeholders, the industry, regulators, and so on. And it sits in the main report, but also as a standalone. It's currently only up there in English, but it will shortly be translated into the multiple languages that represent the OES-Environmental countries, which includes countries all across Europe, one African country, North America, Asia, and Australia. And finally, there's a set of what we call short science summaries. These are two-page, back and front, with lots of pictures, nicely laid out, with very top-level outcomes for most of these chapters I'm describing to you. And we see these as really being aimed at the interested public and the policy level of agencies. And again, they are online and downloadable. Okay, moving into Chapter 2 in the introduction, this is where we define stressors and receptors and the way that we look at these interactions. It also puts forward the idea of how monitoring around these devices needs to be question-driven. We are really interested in things like the importance of scale. For example, when we think of mooring lines from a device in the water and we think of the scale of whales, it starts to give us answers about whether whales are going to become entrapped or entangled. And there's many other sort of geographic and also temporal scales that come into account here. Most of the research and monitoring that's been done in this field to date has revolved around two different types of monitoring questions. One are those mechanisms for potential harm. For example, animals approaching a turbine, how close will they get? What is the likelihood or the mechanism for what they might be hit by a rotating blade and injured? What kind of effects of radiated noise would affect animals? These are types of investigations that can be, to some extent, taken from one location to another and really inform a new situation. The other types of questions that have been investigated at considerable depth is the context for risk. And that is, for example, if you had a tidal turbine located at depth, what is the density of the animals of concern at that depth so that they might encounter it? If you look at a new location, what is the presence of certain species which are at risk? Maybe they're endangered in the U.S. terms, species at risk in Canada, or falling under the directives in Europe. So these are the sort of investigations that we've gotten to date that help to inform what we know. Moving into Chapter 3, collision around turbines. This is perhaps the meatiest chapter in the report, and that is because this is the hardest thing to solve. We look at the potential for collision risk for marine mammals, for fish, for diving seabirds around tidal turbines, and also turbines that go into large rivers. These are not conventional hydro dams, but sitting in the run of the river with the same kind of technologies you'd use in a tidal race. And the reason this is so difficult is there is no proper analog. It's not like a hydro turbine. It's not like a boat propeller, a ship propeller. And even though we have been looking at this for a 10-year or more period, we still have very few observations of animals very close to turbines. And a later chapter, I'll get into that a little more, but they're just very, very difficult to see what's really going on. It's also interesting to note that depending on what country you're in, certain animals are valued, shall we say, more than others. In Scotland, marine mammals and diving seabirds get the most attention, whereas if we move to the U.S., Canada, Japan, or Wales, it becomes fish. So we need to be able to recognize how all these different species and species groups might interact with turbines, and we have a hard time seeing them. We've done a lot of modeling of collision risk, but frankly, the models themselves aren't that great, and they need improvement, and we have very little data with which to validate them. So what you're seeing here, this little dial on the right, you're going to see a number of these in subsequent slides. This little odometer is trying to give a quick snapshot that we can look at over time of what the risk is considered to be to animals from collisions with turbines. And it's the typical green, yellow, red. With the fairly high, orangey kind of location of this dial, this indicates this is still considered to be a fairly high risk, and that is largely due to uncertainties. Risk is made up of the probability of something happening and the consequence, or how bad it might be if it happened. We are very uncertain about the probability of collisions of animals with turbines, and we don't really understand if a collision occurs, how bad the outcome might be. Injury, death, a recoverable injury, not really known. So this keeps the risk quite high for this one. Underneath, you see four gray bars, and these are our way of communicating what needs to be done to decrease that uncertainty, to move forward with our understanding of risk and perhaps lower that risk, we need to increasingly share the information we have, make sure that regulators, developers, and others around the world have the same set of information. We need to continue to improve upon our modeling of this interaction, this collision interaction. We need monitoring data desperately to verify the findings, and there's still new research that is needed. Moving into Chapter 4, this is the risk from underwater noise, and this is operational noise from devices operating in the environment. It is not installation, pile driving, and so on. We know a lot about pile driving in the marine environment and the damage it can do, but that is quite well regulated in other industries, and it's very transferable here. But the sound of these tidal turbines and wave energy converters, how it might affect animals, matter. And why do we care? Because marine animals use sound in the ocean the way we or terrestrial animals use light and sight on land. This is how they communicate, navigate, and so on, search for prey and so on. Oh, and I'm very sorry, I meant to mention at the bottom of each of these title pages, the authors are listed. I missed the first one, but this is Brian Pelagic and Chris Baffett at the University of Washington actually wrote this chapter on underwater noise. So the risk from underwater noise. The first and foremost concern about underwater noise, like loud sounds like pile driving, is actual physical harm to animals. And the sound coming out of operational MRE devices is not that loud, so we really can sort of discount that. But beyond that, the concern is changes in behavior of animals, and this might be detrimental to their health. So we would think we want to look at behavioral changes. These are really difficult and costly to investigate. However, recently we have been given two very nice tools. There is an international standard under the International Electrotechnical Commission, known as TC-114, specific for marine renewable energy. And this is a standard to measure underwater sound from wave energy devices and turbines. We further, in the U.S., and really nowhere else in the world we can find, we have some action thresholds for underwater sound for marine mammals, which are put forward by our National Oceanic and Atmospheric Administration, and that allows us to understand what levels might be harmful. And the Bureau of Ocean Energy Management, another U.S. federal agency, has guidance that also do the same for fish. So we have something against which to measure and good techniques for doing so. So to date, any of the turbines or wave energy converters, that's WECs, one more acronym, have fallen below these guidelines and standards. So that gives us heart that this may not be a very big risk. So what you see in the dial there is this risk has come down considerably from where we were at collision risk. We think it's, still a risk, but it's not a great one. And to get forward further towards understanding the risk and decreasing uncertainty, we need to increase our sharing of information, increase modeling, improve our modeling. Most of all, we need monitoring data to verify these models and some new research. Sorry, something. There we go. Okay, Chapter 5 is the risk from electromagnetic fields. Now, this is looking at EMFs, electromagnetic fields, produced by the operation of marine renewable devices, particularly the export power cable that would take power back to shore. And the issue is that some species, and only some species of marine animals, are sensitive to EMFs. Many, many do not have the sensory equipment to even recognize electro or magnetic fields. They tend to be a certain number of benthic invertebrates, things like crab and lobster, some of the elasmobranchs or the cartilaginous fish, like some species of sharks and skates and rays. So because only some of them are sensitive, it becomes very species specific. We have a number of lab and field studies not directly related with marine renewables, but reproducing those conditions as much as possible. What these show is that these sensitive animals recognize an electromagnetic field. They may change their behavior, but it does not appear to be sufficient to be harmful. Typically, a sensitive animal swimming near an energized cable will take note, perhaps slow down, but then continue on its way. However, right now we don't have many marine renewable energy devices in the water, so the amount of power that's being carried by any of those cables is quite low. As we develop out into large commercial arrays of devices in future, this may need to be revisited because it's really an additive sort of force. Unfortunately, we have no thresholds, regulatory thresholds anywhere in the world, and no standardized method for measuring EMFs in seawater and in bottom sediment. So we are a little hampered there. But overall, we consider this to be a fairly low risk, simply because the amount of power being carried by marine renewable devices, especially now with 1 or 2 or 3 devices, is very low. And you see that reflected in the dial down in the green. We do need to share our information very widely, improve our modeling, need more monitoring data to verify the models, but it's questionable whether a great deal of new research is needed to further understand this issue. The next chapter deals with changes in benthic and pelagic habitats. That is, as soon as we put devices in the water, it may be foundations and anchors, it may be on the bottom, it may be mooring lines and buoys up through the water column. We are going to make some changes in the benthic, the bottom, and the pelagic, the open water habitats, and this will, of course, have some effect on the animals that live there. However, this is a situation where many other offshore industries can really inform us. There's there's a lot we can learn from things like navigation buoys moored in the ocean, the various placement of oil and gas rigs, the floating rigs, and also oil and gas exploration and so on. So what the bottom line here is, if we site MRE devices well and we avoid rare or unusual or fragile habitats, we probably will have a very small footprint on the bottom habitats as well as those in the water column. Now, the other thing that happens when you put something in the ocean is many species of fish will go and reef around it, hang out around it, and biofouling organisms, that is larvae, will settle and grow. As humans, we call it biofouling, and we don't like it because it interferes with our sensors, it interferes with our equipment, it sometimes makes it very hard and heavy to do the work in the ocean. But this is not really an environmental issue. It has been theorized that we might be encouraging non-native species to settle in this matter, but there are as yet no studies that show that. So based on that information we can get from other industries and proper siting of devices, this really seems to be a pretty low risk. So the way forward really is to increase the sharing of the information we have. We still need some better modeling and so on, and every location in the ocean will be a little bit different, but we know a great deal about these mechanisms. Chapter 7 deals with changes in oceanographic systems, and that is what happens when you put devices in the ocean and flows change and wave heights change and so on. You worry about the circulation and wave height change, et cetera, not really due for those primary reasons, but for the secondary knock-on effects. For example, sediment transport patterns may change, which could change habitats, sand transportation, et cetera, and perhaps water quality and ultimately marine food webs. However, for the small numbers of marine renewable energy devices that we have in the water right now, these changes in physical characteristics of the oceanographic systems are way too small to measure. They would fall within the natural variability in the system, so we don't measure them. What we do is we've learned from numerical computer models what might happen when we put these devices in the ocean. But in order to get any kind of response from the ocean, it's necessary to put many, many more simulated devices in, tens and hundreds and thousands of turbines and wave energy devices. And once you try to propose that, you probably won't get the chance to do that in real life and for other reasons. Now, these models, and there are many, many, many of them throughout the world, on the whole have not been validated. So we still do really need to do a better job validating them. But at this point, based on these studies, particularly for 1, 2, 3 or so devices in the water, we consider this risk to be very low. And what we need to do is share this information, maybe do a better job with our modeling. And certainly when we go to very large commercial arrays, maybe we will be able to measure changes, and that will need to be revisited. Okay, Chapter 8 deals with encounters with mooring lines. The concern, and this has been a concern among stakeholders, that these lines through the water column could entangle and snare and trap large marine animals. Now, the concerns are really based on two outcomes. The first is when submarine cables were first put down in the ocean close to 100 years ago, they were put down with a great deal of slack, and it was found that they could loop, and actually there were whales looped and drowned from these cables. That kind of system was corrected quite quickly, and we haven't seen anything like that in modern times. But we do continue to see whale, dolphin, basking shark, and other large animal deaths from fishing gear that has been abandoned or gotten loose. And that is because it's wrapped up the animal, may cause it to drown if it's a marine mammal, or it may simply make it impossible for the animal to feed or do the other things that keep it healthy. But we need to understand there's fundamentally a difference between loose fishing gear and marine renewable energy lines and cables. First of all, there are no loose ends to wrap around. And the mooring cables and even the cables between devices, as you see in this drawing here, are simply too, there is not enough slack to form a loop that one could ensnare an animal around. So we consider this risk to be very low. Again, we need to share the information we have. We probably need to be able to model it a little better, but we do not consider that this is a real issue. And you can see this is where this idea of scale comes in. We also know a lot of these animals are pretty good at detecting things in the water column. Okay, so that's the end of those classic stressor-receptor kind of interactions in this report. The next chapter deals with social and economic interactions. We have not gone into this in great detail, but what we have focused on is the fact that any time one wants permission to put a device in the water, there's environmental regulations in every country, and there is the need to collect data on social and economic background and effects that might ensue. So it's really important that for a project area, the social and economic interactions are documented, and then the potential effects are projected. The kinds of data that need to be collected are things like, if you brought a new industry to a remote area, what would the effect be on schools and social services and cultural areas? And also, what would the economic effects be on employment and wages and businesses and infrastructure? And these are all necessary things to put an application in for consenting or a permit, and yet there's no guidance to do that. So we've tried through expert opinion and elicitation to put together that sort of necessary list. We've gone further to suggest that not only does this need to be done for consenting or permitting purposes, but that there needs to be follow-through with this industry to understand if these effects or benefits were really derived. And we believe that at the project scale, the marine renewable energy developer needs to be responsible for collecting the information initially and tracking it over the life of the project. But there is a need for more regional or strategic level of information, and that really falls to the governments, the municipalities, the regional governments, and the national governments. Okay, moving into the next section of this report, this is one chapter in the section on environmental monitoring. This was written by Dan Hasselman, who wrestled this entire list of authors you see here. These are probably the best expertise in the world on this issue. What we have looked at is monitoring technologies and methods for studying animals interacting with tidal turbines. It's not all kinds of monitoring. A lot of that is contained in these other chapters. But as I mentioned, this whole thing of colliding or animals coming close to a turbine is a really, really hard problem. So what we do traditionally in this field is to use a suite of instruments to try to observe what is going on. We first use passive acoustics or hydrophones in the water to listen to vocalizing marine mammals, those that do talk, and also to get a soundscape for the project area. We use active acoustics to get an acoustic image, a sound image. These are different types of sonar, single beam, echo sounders, multi-beam, acoustic cameras, and so on. These insonify an area with sound waves and then look at the return. We also use optical, video, and still cameras to try to get a better sense of what the species is and what's really happening. And many of these devices are packaged together in integrated platforms that are put down in the ocean, and they will have an integrated data acquisition system to try to bring it all together and try to understand from these different sensors. We're looking for different pieces of information on the same target with these different sensors. But this is really a hard problem because these are extremely high energy waters moving fast. It's a tough place to operate and keep gear in the ocean. Often the waters are turbid or murky, so you may need to use lights with your cameras, which change the behavior of animals. Biofouling becomes a real problem when you put these packages down for any length of time, especially over things like optical ports, lenses. Now, as we're collecting this kind of data, especially video data, but also the acoustic camera data, we get huge, huge amounts of data, which result in very large data mortgages that we simply can't deal with. So we try to look for ways to pre-process or make choices on board before taking all the data and storing it. And this requires, among other things, very careful power management. Most of these devices go out and are put on the bottom or somewhere in the water column dependent on battery power. So you really have a very limited amount of sampling and observations and data collection that you could do. So this chapter is really rich, and I would really recommend you take a look at it if you have an interest. There's about 4 or 5 of these kinds of integrated platforms existing in the world, and each is described in there. Okay, now we're moving into another section looking at the management and planning tools that seem to be quite valuable for marine renewable energy development. The first is Marine Spatial Planning, written by Andrea out of Ireland. And this is really how you use marine spatial planning to interact with and help the marine renewable energy forward. Now, Marine Spatial Planning, MSP, is a process that balances the needs of ocean users and ocean uses, so you get that triple bottom line of environmental, social, and economic benefits for all. Most of these processes are based on the collection of geospatial data on marine resources. That's everything from the energy resources in the ocean, the living animals, the habitats, the uses, and so on. For this chapter, Anne-Marie surveyed the OES-Environmental nations about their marine spatial planning programs, and what she found was that MSP application really varies by country and sometimes within a country. We have countries in OES-Environmental who have very well-developed marine spatial planning programs that include marine renewable energy siting and development. Others may apply some MSP principles but not have real plans, and some haven't yet gotten to that. The next chapter deals with adaptive management, another method of trying to move forward with consenting of MRE devices. Adaptive management comes out of other fields, other industries, and natural resource management, sometimes called learning by doing, where one puts devices in the water, monitors them, learns from the monitoring data, and makes changes accordingly. That's what that little loop thing on the right is, that you would assess a problem, design, deploy, monitor, and then, sort of loop back to see if you've made changes. This is not give it a try and see what happens. It's a very structured, iterative management process where there has to be real commitment from the developer, the government agencies, and stakeholders to really meet regularly, to look at monitoring data, and to make recommendations for changes. In some cases, the amount of monitoring could be increased if there's a need for better resolution, or it could be decreased if it's clear the risk is low. And we do see really several marine renewable energy projects that have been forwarded worldwide by the use of these adaptive management processes, and there's a whole set of case studies in this chapter that outlines those. Chapter 13, Risk Retirement. Now, this is a product of OES-Environmental, and the point here is to use information from already consented projects to inform new project applications. for certain stressors under certain conditions. The idea is to try to not reinvent the wheel and do every study at every location. But by applying this knowledge, data from permitted projects, we also look to research studies and analogous industries. We try to really get a proportionate amount of data collection required for the risk associated with whatever the device is doing. It's important to note this doesn't replace or change any regulatory processes. This is really trying to make information readily available so it can be used in these kind of situations. This process was developed internationally, and we've looked at two stressors so far. We looked at underwater noise, and we looked at electromagnetic fields. And this is for these 1, 2, 3 devices in the water now, not for much larger commercial development. But it was felt by the experts that we are very close to being able to retire these risks, meaning they won't need to be investigated at every new site. But that said, there were some caveats. For example, with underwater noise, we need to get measurements as new types or designs of devices come ready for deployment, because they may make different sounds. We also need to understand better how much power is carried in what kind of configuration of electrical cable to produce what levels of electromagnetic fields. So there's some things that still need to be done, but we think those are very close to being retired. We do this by making data sets readily available from already consented projects, a term we've called data transferability, where the developer, the regulator, the stakeholder can go in and look at a new project and say, what else is analogous? What other projects have been developed that have the same species groups, the same kinds of environments, the same habitats, the same devices, and bring those data sets to bear. Okay, the last chapter in this report, the summary and path forward, really deals with, what's next. And there's a whole series, sort of a workup to this, but there are really 4 main principles we're trying to put forward as a path that will facilitate consenting or permitting. First, the belief that data collection that is requested at projects really needs to be proportionate to the risk. And that may seem obvious, but that has not always been the case. There needs to be sufficient evidence of risk or likely risk for regulators that they can really rely on and understand once we have that sufficiency of risk, of evidence to move forward. We are really trying to promote this idea of transferring data and information from already permitted projects and other studies for use and making that readily available. And finally, that we need to move to retire these risks where there really isn't a significant risk, because this will allow us to concentrate our time, our resources, our energy on those real risks and try to understand them better. But again, we are relying at this point on what we know from 1, 2, 3 devices in the water, not larger arrays. And much of this may need to be revisited with larger arrays. Some of it may be very applicable, but some may not. Okay, I just want to note again, as I said before, there is additional content from some of these chapters. They tend to be more detailed technical explanations and tables. In some cases, there were much longer versions of the chapters, which didn't really fit the book, and they're online. The executive summaries up there, and the short science summaries, and they're all posted at this point for download. And they're posted on Tethys, as you'll see from that link I showed before. If you're not familiar with Tethys, this is our knowledge management system that was developed and maintained at Pacific Northwest National Lab. It is a Drupal site. It's got over 6,300 scientific papers, gray literature reports, other documents. It does look at marine energy. It also looks at land-based and offshore wind. But in the marine energy space, there's a great deal of information there, and you can go in and search this knowledge base as you would like a database, filtering and so on. You can also examine it through the map viewer, which is a geographically based information. Tethys Blast is our bi-weekly news blast that will inform you about new things going on, and been added to Tethys, news and events, funding opportunities, sometimes job prospects, et cetera. Then we have other things, stories, calendars, et cetera, that I think you'll find informative. So if you're not familiar with Tethys, please go visit. It's just tethys.pnnl.gov, and I think you'll find a lot of information there. And this is the site where you can download the State of the Science report. If you go up to that little gray box in the upper right, sort of on top of the ORCA there, that'll take you directly to the State of the Science report page. Okay, now I mentioned that I'm the one doing all the talking today, and my colleague Lene Hemry is on the line as well. But this is really a huge group effort, a village effort, if you will. This is my PNNL team, who have been just wonderful and done a huge amount of work. And then here are the chapter authors sort of listed in the order in which they appear. This is an incredibly talented group, and I cannot say enough about their expertise, their experience in this field, their professionalism, and their real commitment to putting together a report like this to really move this industry, concerned stakeholders, and others forward. So I do want to note that we have some more webinars coming up. Next week we will have a webinar, and it'll be 8 a.m. Pacific time, so 8 hours earlier than this, or 9 hours earlier than this one. And in this one, these next webinars, you will hear from the chapter authors in much more depth than I've just given you sort of a skim over the surface. There will be 5 of these key interactions talked about on the 17th: underwater noise, EMF, changes in habitats, oceanographic systems, and mooring entanglement. And then on June 22nd, we will focus in on the collision risk for marine mammals, marine mammals, fish, and seabirds, and also on the environmental monitoring technologies around these turbines. As I mentioned earlier, we consider this a public draft that's just been released, and we'd really like to hear if you have any comments on it. We'll take public comments until August 10th, and it's a Tethys email you respond to. It's in the report, and we will release the full book in September. And there's the download address too, but you can find it pretty easily going to Tethys. And I believe that's it. I would just very much like to thank you for getting online with us here today. If you do have any questions, we'd be happy to open the phone lines if you would like to ask a question, or write it in the chat box. And even if you think of some of these things afterwards, please don't hesitate to reach out to me, to Lene, to any of the group. We are recording this webinar, and it will be posted on Tethys in another week or so in that same area, State of the Science area on Tethys. So if you missed this, or you thought your colleagues might like it, please visit there. So with that, Oneida, maybe you could open the phone lines and see if anyone has a question.
Thank you. If you would like to ask a question, please select all panelists from the drop-down menu in the chat panel, enter your question in the message box provided, and send. You may also press #2 on your telephone keypad. You will hear a notification when your line is unmuted. At that time, please then state your question. Once again, pressing #2 on your telephone keypad will indicate that you wish to ask a question. Thank you. And there are currently no questions in the queue. Once again, if you would like to ask a verbal question, please press #2 on your telephone keypad. Thank you.
Well, we have a question here about if we understand how animals interact with one or two machines, why can't we understand what will happen when there's a big commercial array? I think the question is basically how much can we extrapolate that information? And it's a great question. I think the answer is we're not sure how much you can extrapolate that information. For example, if you had a device that was putting out noise, let's say you had 3 of them, and you could understand the sound field and how it might affect animals, you might be able to, with good modeling capabilities, then understand what the sound field would be at 10 devices. and perhaps that would just give you a sense of whether animals would enter the area or not. However, if you had 1 or 2 devices and animals were avoiding rotating blades, they were trying to not collide with them, what happens when you then suddenly have 10 devices? Does the animal see each device individually and have to kind of navigate through them sort of like a, pinball machine? Or do they look at a whole area as being something of danger? So we don't know for many of these kinds of stressor receptor interactions how extractable that information is. We may just have to examine some of these again when we get to commercial arrays.
There are currently no additional questions in the queue. Once again, if you would like to ask a verbal question, please press #2 on your telephone keypad to enter the question queue. Thank you.
Okay, it sort of sounds like no one's got burning questions at this time. Please feel free to reach out to me, to Leneg, or to any of the others who have been associated with this, this report at any time. Oh, wait, I do have a question. Hold on. Okay, the question is this. Across the various categories of risks and impacts evaluated, did the analysis singularly evaluate examples from existing modeled renewable energy systems, or were there resources examples drawn from other existing sectors? Thinking of the comparison that was drawn around loose lines from fishing gear. Yeah, thanks very much for that question. And again, it depends. Underwater noise is certainly something that happens from other systems, and we have compared some of that to, say, the sound of vessels, of big ships going by, but we find that the nature of the sound from the marine renewable energy devices is somewhat different than that of ships. So that's not a great comparison, and the tidal turbines turning and potentially striking animals, we have no analog for. A ship propeller runs much more quickly, much faster than, say, a tidal turbine, and the ship can change direction very quickly, which a turbine, of course, does not. So that's not a great analog. However, if we think about electromagnetic fields from cables, we certainly have lots of examples of those in the ocean, from telecom cables, power cables from mainlands out to islands, offshore wind cables. So those we certainly have drawn from those industries where possible. The same is true for habitat, as I mentioned, or the loose lines from fishing gear. There you see the contrast. So we've had to take each of these stressors, and in many cases a specific stressor receptor interaction, and really look at it individually. We hope that we are putting down enough information that nobody will have to go back and do it to quite this degree again, but I guess this is really how you build that knowledge base, I guess. So thank you for that question.
Thank you, and it appears we do have a verbal question. Caller, please go ahead.
Hi, Andrea, it's Jesse. How are you?
Hey, Jesse.
Hey. Yeah, thanks. This is wonderful. I'm so happy that the State of the Science report is out, and I'm on my phone, so I couldn't figure out how to write in a question. So, anyways, I know it's getting recorded, but I was curious if you have gotten a lot of feedback, interactions with the regulators when you introduced the idea of risk retirement, which we all are striving towards, but I haven't personally seen a lot of use of that word in other industries and so forth. And I'm just kind of curious if you could describe how that's going with the regulators.
Oh, that's a great question. And if you have 2 hours, I'd be happy to tell you. No, only kidding. We have done a whole series of meetings with regulators in the U.S. because we're U.S.-based. We started it here, and the process is slowly working out through the other countries. We started by surveying regulators very broadly across the U.S. as to what they knew about wave and tidal devices, what they believed the greatest risks among these stressor receptor interactions was, and so on and so forth. And then we based what we how we move forward with risk retirement, data transferability on those answers. And we have done a whole series of workshops with regulators, taking them through this process, which is sort of a long, tedious process, bit by bit, and asking for feedback and incorporating that feedback. And we have generally found with the regulators, they are quite accepting once we say this is what risk retirement is and this is what it is not. We are not presuming to tell any regulator his or her job, and we are simply trying to make readily accessible information that already exists and find a way to apply it to new systems. Beyond that, that was sort of the theoretical end. We went with underwater noise and EMF, and we assembled the evidence base and presented that at a number of workshops with the scientific community, with a few regulators, a few developers, and really asked them to tell us whether they felt this risk retirement for small numbers of devices based on this evidence was viable. We sort of said, you're the jury. Tell us if we convince you. And I think we've gotten really good traction, but it's been a slow process, and it sort of has to be done at a retail level, practically a few regulators at a time. So I think we're making some progress. And by the way, risk retirement has been thrown around in this industry, but we found it's actually been used in some other industries. I have some references. So that was kind of a relief as well. So that's kind of a long-winded way of getting at that, Jesse. We think it's quite promising, but we're still working hard on it, and it's going to take time.
No, that's great. Thanks for the answer. And I know just it sounds just like the word or the concept just requires a definition every time it's used because it can be interpreted funny. So who knows if that can evolve over time? But that's great. I mean, ultimately we want to get there.
Yep, and I will note that particularly in the UK and Scotland, which has the greatest development of marine renewables in the world, they have really embraced this idea of risk retirement and a number of other things. I think because the regulators have a great deal more experience, they feel more confident in what they have available to them, and so it's been really helpful to look to some of these other countries and the way that they are progressing towards this.
Yep, thanks.
Okay.
Thank you. And once again, if you would like to ask a question, please press #2 on your telephone keypad. Thank you. And there are currently no additional questions in the queue.
Okay, well, I think I will give everybody some time back. And I would like to thank you very much for joining us today and those thoughtful questions. And please do go look at the State of the Science, the full book, the short version or the shorter version. So thanks so much, and we look forward to having you join us on some of our subsequent, let me see if I can go back there, the subsequent webinars next week and the following week. So thanks very much, everybody.
That concludes our conference. Thank you for using Event Services. You may now disconnect.